Welcome to Module 4, Well Control during Drilling Operations. By the end of this module, you should be able to define some important terms used in well control, describe how kicks happen, recall how kicks are detected, identify the first actions to take when a kick is detected, describe how to make the well safe, and recognize the key roles and responsibilities during a kick. This module consists of 5 chapters. They are definitions used in well control, how kicks happen, monitoring, detection and first actions, making the well safe, and roles, responsibilities and empowerment. Each chapter will end with a short knowledge check to confirm your learning. Chapter 1. Definitions used in well control. When discussing well control, there is a whole glossary of terms used in the oil and gas industry that you may not be familiar with. Let's start by defining some of these terms. The wellbore is the actual hole that has been drilled. This includes the open hole being drilled and the cased hole section above it. Well control, sometimes referred to as pressure control, is all about controlling the pressure from the formation. When the well is being drilled, the pressure is controlled by the column of drilling fluid. As long as the pressure pushing down from the drilling fluid is greater than the pressure pushing up from the formation, and no pressure is seen at surface, then we know the formation pressure is being controlled. As we learned from previous modules, this is referred to as the primary barrier. The secondary barrier refers to the blowout preventers used if the primary barrier fails to hold the pressure. Whilst the well is in the production phase, the well pressure is controlled through the Christmas tree, unless there are well intervention operations taking place. During well intervention, for example when using slickline or coiled tubing, additional equipment is used to maintain pressure control. No matter what is happening with the well, be it drilling or well intervention, the primary barriers are there to prevent a blowout, and if they are ineffective, then the secondary barriers come into play. For the secondary barriers to be effective and stop a blowout, the equipment must be fit for purpose, and the people operating it must be suitably trained and competent. Any signs of loss of primary well control must be quickly recognized and acted upon to stop an event from becoming uncontrollable. As ever, prevention is better and easier than cure. Hydrostatic pressure is the pressure exerted by a fluid which is not moving. In fact, the word hydrostatic is derived from hydro, meaning fluid, and static, meaning not moving. Hydrostatic pressure is critical to well control. As we have already learnt, primary well control is maintained by the provision of a column of fluid, the drilling mud, that exerts a hydrostatic pressure equal to or greater than the pressure contained in the formation. Let's take a closer look at hydrostatic pressure to get a better understanding of what it means and how it is used to control formation pressure, the pressure found within the formation. Hydrostatic pressure is the force created by a column of fluid which increases in proportion to the depth from the surface because of the weight of fluid above it. As shown in the diagram, the increase in pressure on the hull of the submarine is caused by the increase in the hydrostatic pressure. Therefore, the hydrostatic pressure exerted by a fluid is dependent upon depth. The same applies for a column of fluid in an oil or gas well. It is important to note that it is only the depth or height of the column of fluid that affects hydrostatic pressure, and that the amount or volume of the fluid has no effect at all. Have a go at increasing the depth of the submarine below surface and observe the subsequent change in hydrostatic pressure. So, is there anything else that may influence the hydrostatic pressure? The answer is yes. As the density of the fluid increases, the pressure exerted will increase. In other words, the hydrostatic pressure will become greater. Imagine a 1-gallon container full of 10 pounds per gallon fluid. The weight of 1 gallon of fluid will be 10 multiplied by 1, which equals 10 pounds. If this weight was acting on an area of 10 square inches, the pressure would be 10 divided by 10, which equals 1 pound per square inch, or psi. If the 10 pounds per gallon fluid is replaced by a more dense fluid of 15 pounds per gallon, the weight of 1 gallon of this fluid would be 15 pounds. The pressure exerted on 10 square inches would be 15 divided by 10, which equals 1.5 psi. We have now seen how vertical depth and the density of fluid affects the pressure at the bottom of a well, and it is the combination of these two factors that give us our primary barrier and thus our well control. To simplify the calculation for finding out the hydrostatic pressure at the bottom of the well, a pressure gradient is used. This simply means that the denser the fluid, the greater the pressure, and this can be expressed as pounds per square inch per foot and is abbreviated to psi per foot. This table shows some examples of pressure gradients for different fluids. If we take fresh water, for example, its density expressed in pounds per gallon is 8.33, and if we multiply it by 0.052, a constant, we find that the pressure gradient is 0.433 psi per foot. Another form of applied pressure we see is formation pressure. This is the fluid pressure found within the pore spaces of the formation. Formation pressure can force fluids into the wellbore. In drilling and completion operations, we use the hydrostatic pressure of fluids, such as drilling mud, to counter the effects of formation pressure and keep the wellbore contained and controlled. In situations where the formation pressure exceeds the hydrostatic pressure of the drilling fluid, there is the potential for an influx of formation fluids, resulting in a well kick and even a blowout. So, formation pressure is the pressure exerted by the fluids in the pore spaces of the formation. That's not as complicated as it sounds. If we attach a pressure gauge to the bottom of a bucket, we see that whilst the bucket remains empty, the pressure gauge will read 0. It's what we call gauge pressure. When we start filling the bucket with fresh water, which has a pressure gradient of 0.433 psi per foot, we will see the gauge rise due to hydrostatic pressure. If we fill the bucket to a depth of 1 foot, it is quite easy to calculate the hydrostatic pressure using the simple formula hydrostatic pressure equals the height, or depth, of the water, 1 foot, multiplied by the pressure gradient of 0.433 psi per foot. That gives us a pressure of 0.433 psi as seen on the pressure gauge. Let's take another empty bucket, but instead of filling it with water, this time we will start by filling it with golf balls. As you can see, the pressure gauge remains at 0. Therefore, even though the weight of the bucket will have increased due to the golf balls, the pressure hasn't altered. Now let's see what happens when we pour the water back into the bucket. Firstly, we don't need as much water to reach the 1 foot level, but more importantly, the pressure gauge is now reading 0.433 psi, the same as it was when there was only water in the bucket. Despite there not being as much water in the second bucket in terms of volume, the height is the same, and consequently, so is the pressure. What has been happening in our bucket is the same as what happens in a porous formation, such as sandstone. This shows us that the formation pressure is only equal to the hydrostatic pressure exerted by the column of fluid. Bottom hole pressure is a term used to take into account all of the pressure exerted on the bottom of the well. Most of the pressure comes from the hydrostatic pressure of the fluid column, so if the mud isn't moving, then the bottom hole pressure will be the same as the hydrostatic pressure. However, if the mud is being circulated in the well, then the pressure exerted to move the mud up the annulus between the well bore and drill string, for instance, has to be considered, as the effect will be to increase bottom hole pressure. The smaller the annulus, the greater the pressure. Any restrictions on surface that affect the flow of mud returning to surface will also add to the bottom hole pressure. There are two conditions that a well may be in, either overbalanced or underbalanced. Overbalanced is when the force exerted by the drilling fluid column is greater than the force exerted by the formation fluid pressure. This condition provides hydrostatic control of the formation fluid during normal drilling operations. Underbalanced is when the force exerted by the drilling fluid column is less than the force exerted by the formation fluid pressure. In normal drilling operations, an underbalanced wellbore is undesirable because we could get an influx of formation fluids into the wellbore, also known as a kick, potentially leading to a blowout. A drill bit can be seen here cutting rock, with the drilling fluid transporting the cuttings back to the surface. In well control, the hydrostatic pressure created by the drilling fluid column must exceed the pressure exerted by formation fluids. Consider a situation where the formation pressure is 5,000 psi. If the well is 10,000 feet deep, filled with mud weighing 10 pounds per gallon, or 0.52 psi per foot, having multiplied 10 by 0.052, the bottom hole pressure would be 5,200 psi. This creates an overbalanced condition, as there is an overbalance of 200 psi. This would be enough pressure to overcome the formation pressure of 5,000 psi and so keep the formation fluid from entering the well. If the same well was filled with water, which weighs 8.33 pounds per gallon, or 0.433 psi per foot, having multiplied 8.33 by 0.052, the pressure exerted at the bottom of the well would only be 4,330 psi. If the formation pressure is 5,000 psi, the well is underbalanced by 670 psi, and formation fluids may enter the well as the formation pressure is greater than the wellbore pressure. An influx is an unplanned entry of water, gas, oil, or other formation fluid into the wellbore during drilling, more commonly known as a kick. For this to happen, the well must be underbalanced. In other words, the pressure of the formation fluids is greater than the bottom hole pressure. The calculation of the volume of any influx is an integral part of standard well control procedures. If the well is not shut in by closing a blowout preventer, a kick can quickly escalate into a blowout when the formation fluids reach the surface. If the influx contains gas that expands rapidly as it flows up the wellbore, this will make the problem worse by decreasing the effective weight of the drilling mud. The definition of a blowout is the uncontrolled flow of formation fluids into the wellbore. This often results in a catastrophic flow of hydrocarbons to surface, and if they are then ignited, the effects can be devastating. Where formation fluids flow into another formation and not to the surface, this is called an underground blowout. However, many underground blowouts will lead to a surface blowout. When we have reached total depth for a particular hole section and need to run casing, we have to trip out, which means bringing the drill bit to surface. This also has to take place when the drill bit gets worn beyond practical use. If there are several thousand feet of drill pipe in the hole, this is no small task. To speed this up, we usually remove 3 sections of drill pipe at a time, known as a stand, and rack it in the derrick. This makes tripping out and back in a much faster process. Even a simple bit change operation can take a whole day to complete, as the entire drill string must be withdrawn from the hole, the bit replaced, and then the entire string fed back into the hole before drilling can recommence. Historically, tripping is one of the most critical times for well control because mud is not being circulated and the bit is not at the bottom of the well. As the pipe is removed from the well, an equivalent volume of mud must be used to fill the well to prevent hydrostatic pressure from falling and the well becoming underbalanced. It is vitally important that we monitor for the correct volumes of hole fill. Chapter 2. How kicks happen. As we have just learned, a kick is the flow of formation fluids into the wellbore. Taking a kick means that primary well control has been lost, and appropriate first actions must be taken in order to regain control of the well. Normally, this would mean closing a blowout preventer and is known as secondary well control. Therefore, all well control equipment must be in perfect working order and the crew fully trained and competent in its use. A kick can occur for a number of reasons. For example, abnormal formation pressure, failure to monitor the well, failure to keep the well full of mud, incorrect fluid density, swabbing while tripping, and lost circulation. Let's take a closer look at each of these. One of the most common causes of kicks is drilling unexpectedly into an abnormally pressured area of formation. This pressure may be greater than that exerted by the drilling fluid, and this will result in a kick. Throughout the drilling operations, the well has to be monitored at all times. Failure to do so may mean that an early indication of an influx of formation fluids and a well kick could be easily missed, and so the opportunity to take fast, effective action is lost. Failure to keep the well full occurs when all of the drill string is being removed from the well and the level of the drilling fluid goes down. The space left by the drill string being removed has to be constantly replaced by drilling fluid. If this doesn't happen, then the column of fluid decreases, and so the pressure exerted at the bottom of the well is reduced and potentially causes a kick. The weight or density of the drilling fluid is restricted to the minimum necessary for well control and wellbore stability, and so is constantly checked throughout the drilling operation using a mud balance. If the weight is too great, it may damage or fracture the formation. If the mud weight is not sufficient, then the well may become underbalanced, potentially resulting in a kick. Swabbing is caused by the reduction in bottom hole pressure when the drill string is pulled out of the well. An analogy is the effect of a piston moving in a cylinder. This results in a decrease in bottom hole pressure. If this reduction in pressure is large enough, bottom hole pressure could drop below formation pressure, allowing formation fluids to flow into the wellbore, in other words, a kick. The expansion of a gas bubble moving up the well further reduces hydrostatic pressure. Lost circulation occurs as the drilling fluid is being circulated down the drill string and back up through the annulus to the mud pits, and the level of fluid goes down. This is because the drilling fluid is being lost to the formation in the open hole section of the well. Sometimes it will only be partial lost circulation, or it can be a complete loss of drilling fluid or total losses. If it is not possible to keep the hole full of mud, bottom hole pressure will be reduced, potentially leading to a kick. Chapter 3. Monitoring, Detection and First Actions. A well-trained, practiced and competent crew is critical to our ability to recognize a kick. Warning signs and kick indicators must be detected and interpreted promptly, and preventative action taken immediately to avoid a blowout. The indications seen at surface come in several guises, and there are key warning signs, so it is vitally important that the crew monitor such things as flow rates and mud volumes for unexpected changes, whatever the activity. As many experienced drillers say, the well will talk to you. You've just got to be prepared to listen to it. Warning signs show changes in downhole conditions potentially caused by increasing formation pressures. Kick indicators are positive signs that fluid is flowing into the wellbore. Warning signs and kick indicators may be caused by factors other than well control, but there isn't time to speculate, as a kick can happen very quickly. If there is any doubt, immediate action must be taken. Upon detecting a kick, the driller will take the appropriate steps for shutting the blowout preventers. Let's not forget that the driller is fully conversant and well practiced in the procedures for this type of situation. This is a very stressful situation, and he has a great deal of responsibility on his shoulders. Nonetheless, it is his duty to do the right thing, and he has been empowered to do so. When the well has been made safe and the situation is under control, then the driller will inform the appropriate personnel. Upon observing a positive kick indicator during any operation, the driller must shut the well in right away using the appropriate shut-in procedure. Whilst procedures differ on different rigs, typically the following would be carried out. Stop drilling or tripping operations. Close the annular preventer or upper pipe rams. Open the upper choke line valve on the BOP. Check the trip tank to confirm that the well is shut in and the flow has been stopped. Normally, the valves in the choke manifold are kept in a closed position. The exact procedure may vary from rig to rig depending upon the exact configuration of pipework. Whilst everyone must be competent in their role and understand their responsibilities, it is important that the decision to act is taken promptly, the correct checks are made, and the information communicated to the rest of the crew. Chapter 4. Making the well safe. The process of making the well safe can be quite complex, and there are many different procedures that can be followed depending on the well and the circumstances under which the kick took place. There are also a lot of calculations that are done to ensure the well is made safe as quickly as possible and that the job is done right the first time. In order to keep things simple, we're just going to have an overview of how we make the well safe and get back to drilling. After the well is shut in, further operations are necessary to regain primary control, and this is known as the well kill procedure. The purpose of the well kill procedure is to get the well back to a stable condition whereby the bottom hole pressure is greater than the formation pressure, at the same time circulating out any formation fluid that is present in the wellbore. Two things need to be achieved. 1. The formation influx must be removed from the wellbore. 2. The correct density mud is circulated around the wellbore. The two most common well kill methods are the driller's method, this is 2 circulations, the weight and weight method, this is 1 circulation. The formation fluid is circulated out by pumping mud down the drill string and back up the annulus, but instead of going straight to the mud pits, it is sent through the choke manifold to control the pressure, maintaining bottom hole pressure above formation pressure. It is then routed through the mud gas separator and then back to the mud pits. When the formation fluid has been circulated out, a kill mud is pumped into the well. This is weighted up drilling mud. The actual weight has been previously calculated so that the hydrostatic pressure of the mud is greater than the formation pressure, thereby stopping any further formation fluid entering the well. When the kill mud has been fully circulated around the well, it is possible to open up the well and restart normal operations. Chapter 5. Roles, Responsibilities, and Empowerment. The drill crew all have their own roles and responsibilities when a well shut-in is initiated, according to the job that they do. The crew will be fully trained and competent to carry out any procedures. On the drill floor, the driller is the focal point for all drilling-related activities, and there are a number of persons reporting directly to him, including the assistant driller, derrickman, and roughnecks. He is the one that will monitor all the relevant parameters concerning the well, and he will be the one that takes all the necessary actions to initially make the well safe if a formation influx is observed. Many people believe that only those working directly on the drill floor have a part to play in ensuring that drilling operations are carried out without incident. However, this is not the case. We all have a part to play. It may be that you see something out of the ordinary at the rig site, and instead of just ignoring it, you must report it to a supervisor. It may be that someone working on the periphery of the industry lends support or understanding after the crew has had a difficult trip. It may be that someone working in logistics goes the extra mile to ensure that the correct people and equipment arrive on site in good time. Think about what your role might be. The dictionary definition of empowerment is to give someone the authority or power to do something. Think back to 2009, when the US Airways Flight 1549 landed on the Hudson River. The captain of the flight didn't ask for permission to land on the Hudson before doing so. Whether or not he would be fired for his actions was not at the forefront of his mind. He did the right thing, and all his years of experience and training came into play, which enabled him to make this landing without loss of life. This was done with the full cooperation and understanding of the crew. In other words, everybody knew what their roles and responsibilities were at the time, and they were able to carry out their job with confidence. It was not only the aircraft crew, but also those in a supporting role on the ground, who knew when it was time to give support and the time to let the captain and crew get on with their workload without interruption. The operation was completed as safely as possible without loss of life or serious injury. But what does this mean to the people that work in our industry who may be involved in a well-controlled situation? The International Association of Oil and Gas Producers, IOGP, said that there is a need to create an operational environment where the obligation to do the right thing is known, authorized, and expected. This is best described as developing a shut-in, then investigate culture rather than the other way round, and not having to seek permission to shut in the well once a well-controlled situation has been detected. This is being developed in the oil field through additional training, and not just the technical kind. It will also include crew resource management, which will provide everybody with the necessary resources to automatically do the right thing when under pressure. So far in this module, we've discussed how well-controlled incidents are caused, largely focusing on downhole issues. We've also mentioned the roles and responsibilities of individuals in carrying out the correct first actions. However, we should remember that the individuals on a drilling installation are all part of a team. Human factors also have the potential to cause well-controlled issues. Human factors refer to the interaction of individuals with each other, with facilities and equipment, and with management systems. Human factors play a critical role in ensuring that pressure control is maintained. It is a broad subject, but non-technical skills, i.e. the cognitive, social, and personal resource skills that complement technical skills and contribute to safe and efficient task performance, can be considered under the following titles: situation awareness, decision-making, communication, teamwork, leadership, and managing stress and fatigue. Let's look at how human factors could potentially cause issues during drilling operations. If, for example, a shaker hand monitoring mud density returning from the well notices changes, they should communicate this with the rest of the team. Not doing this could result in a serious well-controlled incident. Not questioning or confirming an instruction which you believe to be wrong could have catastrophic consequences. Well done, you have reached the end of this module. You should now be able to define some important terms used in well control, describe how kicks happen, recall how kicks are detected, identify the first actions to take when a kick is detected, describe how to make the well safe, and recognize the key roles and responsibilities during a kick. It's now time to take the final exam, where a pass mark of 70% needs to be achieved. Take your time, and only click the Submit All button when you're happy with your answers. If you fail, you will be able to resit the exam. You're advised to review the module before doing so. Thank you for completing this training module. We hope this will help you in your workplace. Remember, you can revisit this module at any time to refresh your knowledge.